So in this screencast, we're going to look at the addition of amines to aldehydes and ketones. So specifically, we're going to look at the addition of primary or secondary amines and the functional groups they form through the condensation reactions. So first, let's look at the condensation of an aldehyde with a primary amine So again, in amine classification, you're looking at the number of carbon groups bonded to the nitrogen. So we just have one. So we basically have NH2. That tells us it's a primary amine. So under these conditions, typically this is promoted by an acid catalyst. We're going to lose the elements of water in the forward direction. And so this is going to condense the primary amine to the aldehyde, losing H2O, and form this new functional group, which is called an imine. So you might see it referred to as an aldimine, so aldimine because it's coming from an aldehyde. So we can also do the same sort of condensation reaction. So I'm going to use a couple more identifiers here, R1, R2, if we're starting with a ketone, and then we'll use R3 for our primary amine. Again, I'm putting this as reversible because these are condensation reactions that produce water. So you can do the reverse reaction by adding water to get the carbonyl containing compound in the primary amine. So H plus minus H2O. So again, we're going to condense the nitrogen onto the carbonyl, losing H2O. That's where this comes from. And now we're going to form an imine derived from a ketone or a ketamine. So an imine is the nitrogen equivalent of a carbonyl group. So because the nitrogen is trivalent, you see we have this extra substituent. Just fix that mistake. This should be R3. So again, this is an imine as well. And so these are imines. Imines result from the condensation of the carbonyl component, either aldehyde or ketone, with a primary amine. So a different functional group forms if you're starting with a secondary amine. So let's go ahead and look at those. So now we're going to look at the condensation of these carbonyl containing compounds, either aldehyde or ketone with a secondary amine. And I'm going to draw the carbonyl containing components slightly different in this case. So I'm going to say, I'll say R1. Now I actually want to show a CH2 group next to the carbonyl. So that's our aldehyde. And so we're going to condense the aldehyde with a secondary amine. So we have 2 bonds to carbon, so that's how we get a secondary amine. Now what you'll notice is we only have HO, so the other H actually comes from one of these, and this is important to note. The carbon next to the carbonyl is called the alpha carbon. And so let me just go ahead and put in, this one has 2, it's a methylene. So we actually identify HHO. So there's where we lose the elements of water in this condensation reaction. So this forms a different functional group now called an enamine. So this is called an enamine. And we can see where that name comes from and the fact that we have an alkene. So there's the En and then amine. So here's your amine here. So enamine. And it's notice the difference of the location of the pi bond or the double bond between the imine and the enamine. So in the imine, the pi bond results between the former carbonyl carbon and the nitrogen. In the enamine, it results between the former carbonyl carbon and the alpha carbon. So this is an enamine. So let's go ahead and look at the ketone case. So I'll just go ahead and show one alpha carbon. And again, we're using these R groups just very generally. So we're losing HHO. Again, let's go ahead and say ketone, secondary amine. Put in these H's here. And again, that's the alpha carbon. So our module 3 is going to focus on chemistry of the alpha carbon, which is important if you're going on to study biochemistry as well. So let's draw our enamine. So put our substituents in 2, 3, 4. So enamine. So here we have the condensation of carbonyl-containing components, and then we're either forming imine or enamine based on the classification of the amine that we start with. So it is pretty confusing. The vowel just changes amine, imine. So one other thing that we have to be cognizant of is that we're forming double bonds. So as we know from alkenes, we can have cis or trans geometry. So what I'll do is in just blue show you the comparison. So for this first imine, so these would be geometrical isomers. In the same sense as we see with a normal carbon-carbon pi bond. So the first one here, these two, if we put in the lone pair, that's going to take the lowest priority on nitrogen. So if we're evaluating each sp2 hybridized atom and we assign priority, so let's go ahead and walk through this. We have carbon versus hydrogen. Carbon has a higher atomic number, so that's going to get the number 1 priority. Then on the nitrogen, whatever this group is, carbon most likely is going to have higher priority than a lone pair, so this will get 1. So we see that across the face of the pi bond, the 1s are on opposite faces. So that's going to be the E, or trans. Isomer. Then over in the other geometrical isomer, we see 1 and 1. They're on the same face, so that's going to be Z or cis. So just keep that in mind, and then you can do the same sort of thing as well for the ketone. We'll just draw out that general structure as we've seen. And for these, depending on what these groups are, you can then assign E or Z to them. So with the sort of just general R groups, we can't really do that at this point. So what about for the enamine? These can also have geometrical isomers. So let's go ahead and in blue, just for comparison purposes, okay, so for the enamine resulting from an aldehyde, so here are the two geometrical isomers. And so for this one here, we have carbon, H. This is going to get number one priority. We have nitrogen, H. This is going to get number one priority. So the number one priority groups are on the same face here. So we're going to go ahead and call this one Z. So Z or cis. And so this one's going to be the E or trans. And again, so number one priority, they're on opposite faces of the pi bond, so E or trans. Let's go ahead and draw the other geometrical isomer for the ketone, enamine. So I guess I have a no. So when we're looking at this, we can assign priorities. So we have carbon H. So carbon is getting the number one priority. So we'll do that for both these here. Then over here we have carbon, nitrogen. So the periodic table is CNOF. So N is going to get priority over C. So this will be 1. So we can then say for this left one, since they're both on the same side, this is going to be the Z or cis. Then this right one over here, this is going to be E or trans. So this has been a pretty general introductory slide about these condensation reactions with the carbonyl component and different classifications of amines, either getting the imine or the enamine, and then a review of geometrical isomers. So on this next slide, let's go ahead and look at the mechanism of imine formation, and then we'll look at the mechanism of enamine formation after that. So imine. So what this tells us automatically when we look at that we have to start with a primary amine. And so for an example, let's look at this aldehyde. So again, you can form an imine from an aldehyde or a ketone, but you have to have a primary amine. So we'll use cyclopentane carbaldehyde, and then let's go ahead and condense that with methylamine. That's a primary amine. And we're going to use acetic acid or ethanoic acid as our acid catalyst. So just by looking at these two components, we can actually just draw what the imine is. So again, this nitrogen is condensing with this carbonyl, so we're losing H2O. We get the double bond to nitrogen and then whatever this substituent is. So there's your aldehyde skeleton, double bond to nitrogen, and then methyl group. So this is an imine. Our byproduct is water, and then our acid catalyst is not incorporated into the product. So what is happening first here? So we're going to do activation of the carbonyl. This is going to be our base. This is going to be our acid. So we're going to protonate this. It's going to be step number 1. So I'm just going to show this as H plus for now. And we know that the conjugate base of that, this carboxylate, is balancing out this positive charge. So this is, I'm just representing this acid in this form because I want to show that the movement of the proton is really what's getting this going. So we'll set up this equilibrium. So we're balancing out the charge there. Now, since we're under acidic conditions, we see that this carbonyl is protonated. Let's go ahead and show that resonance form so you can see why the carbonyl gets attacked. And, recall the discussion of acetals. So here's a resonance form. So this is telling us the carbonyl, carbon is positive. So we have an electrophile in the presence of a nucleophile. We just balance out the charge here. So here comes the methylamine now. That's going to form our carbon-nitrogen bond. Notice now the nitrogen is positively charged. So this is a good example of when we're looking at mechanisms, like where we're at and where we need to be, so we can just take inventory of what we need to do. So notice now this carbon is sp3 hybridized. We have OH, we have this nitrogen that's positive. We need to get from here to there. So we need to do that in a very rational form using things that we've learned thus far in Organic 1 and Organic 2. So you notice we have to form water. So we don't quite have water yet. Notice that this nitrogen no longer has these hydrogens. It's neutral, and then there's a double bond. So that's all the things we have to do. So I'll write this in a stepwise fashion so we don't do too much at once. We're going to have this conjugate base, abstract an acidic proton. So now we're at neutral. I'm going to draw our acid down here, H plus, conjugate base there, balancing it out. So this molecule at this point here, notice the oxidation state. You have 2 bonds to heteroatoms. If recall from the last screencast, if both of those were oxygens, it would be an acetal. But since one is nitrogen, one is oxygen, this is called an aminal. A little bit confusing, not animal, but aminal. So again, moving forward, we got to get rid of that oxygen. So what do? We're going to protonate it. And again, writing these mechanisms out, it's pretty long, but it helps you understand how the protons are shuffled about. Oxygen's now plus, this conjugate base is minus. We're balancing out this charge. What happens next? We have nitrogen lone pair. It's going to do an elimination to remove water. So this is where we form the water in the reaction. So remember, an elimination is formation of a pi bond. So getting rid of water is good because it's a small neutral molecule. So nitrogen plus, and we have our conjugate base minus. So what do we need to do to get from here to the final product? We're simply regenerating our catalyst at this point. So the conjugate base abstracts this acidic proton. We break this bond, put the lone pair on nitrogen, and we end up back at neutral species. And just show our acid that's reformed. So as you can see, I mean, we're drawing 1, 2, 3, 4, 5, 6, 7 steps, all that's happening from the starting materials to this product. That's what's going on. It is useful to see this and to draw it out because you see how the presence of this catalyst, acid catalyst, is really involved in proton transfers. And again, as I mentioned, if you're going into biochemistry, that's very important to see how enzymes work. This is what they're doing is just shuffling these protons around to activate the functional groups. So in our next slide here, we're going to look at the mechanism of enamine formation. And so what this necessitates is that we have to use a secondary amine. We can use aldehyde or ketone as the carbonyl component, but we must use a secondary amine. So for this mechanism, let's go ahead and use cyclohexanone. So this is a ketone. And for our secondary amine, we'll use this compound, which is called parolidine. So it's a nitrogen heterocycle. It's a secondary amine. For our acid component, we're going to use this acid, which is a sulfonic acid called Paratoluene. Sulfonic acid. It's abbreviated PTSA. So Just by looking at these words and looking at these structures, we know the product is an enamine. The skeleton of the ketone remains intact. So we have to form an enamine. Carbonyl carbon, let's just designate it there. We'll put a double bond there. That's the ene. Now off that is the amine, which is this part. So we have the nitrogen and then whatever is bonded to it. So this is the enamine. And enamines are going to be very important to us again in Module 3. So everything in this course is really building up. You know, we can't really just forget the concepts that we've learned. So let's go ahead and kick off the mechanism of how this happens. So I'm going to designate again this carbon here is alpha carbon. This carbon is also alpha. And I want to make a point here. The cyclohexanone is symmetric. This alpha is equal to that alpha. There will be cases where alpha and alpha are not the same, and so we'll just use we'll call one alpha prime. But these are both the same, so we're just going to pick one. I'm going to actually show one hydrogen here, just so we can see HHO. That's where we lose the H2O that comes as part of the condensation. So again, the first thing we're going to do and again, I'm just going to abbreviate, you know, the rest of this part of the molecule, the conjugate base of that is A minus. We're going to protonate the carbonyl. So we've activated the carbonyl. I want to show you the resonance form so you can understand why the nitrogen is attacking. Plus, so that's how we get to the resonance form. We now have electrophile, nucleophile. The nucleophile attacks the electrophile. So you can see at this point, we have 1, 2. We're still retaining those 2 bonds to that carbon. This is basically a protonated aminal at this point. Remember, we saw that term. So what do we need to do, again, to get from here to where we're going? We have to get rid of this. We cannot have it leave as hydroxide anion because we're in acidic conditions. It has to leave as water. So in a stepwise form, let's get to doing that. Conjugate base abstracts that proton to regenerate the acid catalyst. And I think you should always show your lone pairs on your heteroatoms as well, because it helps you keep track of them. So let's go ahead and we'll put H plus A minus. So now we're neutral in this aminal species. Let's see that word again, aminal. So the scientific literature will also refer to this as an NO acetal. So these are all like synonyms of one another. So what we'll do now is we'll have the oxygen get protonated again. So we're going to make that a good leaving group. Plus charge migrates on to oxygen. We balance it out. Nitrogen is going to do the elimination of water. So here we lose water. Now we end up with this. And so this is the key difference in why that alpha carbon is important. So at this point, this is a salt. Another term for this would be an iminium ion. So it's a salt because you have plus, minus. Another term is an iminium ion. Now let me show you a resonance form of this. So now nitrogen neutral. And this is where that alpha carbon is important. So again, let's just put in that alpha, because we need to regenerate the catalyst, right? So we have to show that mechanistically we have our base abstracting that proton to do an elimination. And that forms the alkene of the enamine. Plus our acid catalyst. So this is an enamine. And enamines are important, again, for Module 3. And so I'd like to show you a resonance form of the enamine, in which the nitrogen lone pair forms that pi bond, and then we put electron density onto the alpha carbon. So this is a resonance hybrid, and this is really important for Module 3, because now we've formed a negatively charged carbon, a carbanion, and we can use that as a nucleophile to react with electrophiles through SN2 chemistry that you've seen to make new bonds. So in this slide, we've looked at the mechanism of an enamine formation. And I think that's what we'll wrap up this screencast with. The next one that we look at, the next screencast, we're going to look at the reductions of imines and enamines to form higher order amines.